this morning session. Okay, so from Tuesday we had the notes on modeling a projectile motion, and we talked about, well, what happens, most of the examples we looked at were a baseball, because that's a pretty common problem to look at. So what happens if a baseball or an object is put into motion by some form, and it takes a special angle from the horizontal. So it's going to go up, and it travels at a special speed, which we're going to call velocity, or sometimes they just use speed. Well, knowing the speed and the angle, we can actually determine the horizontal distance and the vertical distance by using these two equations. So, just to quickly reconnect, and those of you that didn't get this from Tuesday, a couple of things notation-wise. When we use this symbol, the absolute value of the vector of v, that symbol is just referring to velocity when it's positive, which is really the speed that the object is going. So that's the big thing. Theta, which is the angle, that's the angle that's formed with the horizontal. So I'm just going to refer to that as the angle. You'll see that pop up when we do different examples. We talked about x of 0. Remember that 0 is when time is 0, so this is the initial horizontal position. And that one you don't often see used very much unless they tell you that something is in a certain spot, 10 yards away, 40 meters away. And then y of 0, since y is dealing with the vertical, the y of 0 is the initial vertical position. So sometimes that's like your starting height. And we'll see an example of that come into play today. So then the only other thing that's kind of interesting to note is the negative 16 is just due to gravity. You may have seen that in some of your science classes. We talked a little bit about it in Algebra 1 and a little bit in Algebra 2 as well. But negative 16 is referring to heat per second. That's the effect that gravity has on. You might also see like a negative 4.8. That would be referring to meters as well. So anyways, that's what we're going to be using. Again, if you haven't taken these notes yet, I would recommend doing a screenshot right now at home so you have access to this. I will also post these notes as soon as we get done so you can go back and look at them on Schoology. All right, so let's start off here. Officially, this is 6-3 day 2, and we're going to look at the parametric equations, how to apply them to solve real-world situations. So, we've got a couple new examples. What I'd like you to do here is you don't have to set up the full, write all of this. We're just going to kind of read the situation, and we'll set up and do the problems together here. But we have Natasha Watley. She was an American former collegiate 4-time athlete, and she actually was the first African American Olympic softball player to play in the Olympics. So kind of a cool accomplishment for her. We're going to take the information here to figure out, in the long run, did she hit a home run? So here's the situation. Let's take this information and we can, I might have to freeze this. I know myself and I know how I write. I'm going to have to change the, okay, that should work. So let's start off with this first part. Our goal is to set up the parametric equations to model the path of the ball. And I just did a quick little screenshot in case you didn't have the formulas from your notes before, but we have to set up a parametric equation in terms of x to represent horizontal motion and one for y to represent vertical motion. So what we're going to look at here is Natasha hit a softball with an initial velocity of 140 feet per second with an angle of trajectory at 23 degrees to the horizon, or to the horizontal, making contact 3 feet above the ground. So just picture her swinging the bat. You can kind of see the bat is 3 feet off the ground when she swings. Important things that you need to know is they give me the initial velocity. So that's 140. You can include the units if you want, feet per second. But I would write that somewhere on your paper just as something that's good to know and acknowledge. And then they tell us that the angle of trajectory to the horizon, so that's theta. And then when we talk about contact above the ground, 3 feet above implies vertical motion. So 3 feet above is talking about this y of 0. Which is your starting height. So number one, we have to find the parametric equations that model the path of the ball. So here's my horizontal motion of a projectile. The projectile is the ball. The first equation, I'm going to add one extra piece to this equation. It's called function notation. It's called x of t, because t represents any possible time. But what we're going to do is we're going to take the initial velocity, which is 140 feet, and we're going to multiply that by the cosine of 23 degrees. So that's this part right here. And then we're going to times it by time. And the important thing is, did you put parentheses around the 23? If you forget those parentheses, then it's going to take the cosine of 23 and the time, and time is not inside of the cosine piece. You got to be careful here. And then our x of 0 is 0. If you think of it, she's going to be swinging from home plate, which means she's at location 0 in a sense. So here's my horizontal motion equation. And that's all we needed to do for part 1, is set that up. Part 2, the vertical motion for number 1 is, now what about how high the ball goes? Because this first equation just says how far it goes. How high it goes is referring to the y values, and t is the independent variable here. So now we're going to take the equation, negative 16, because everything is in feet per second, the negative 16 is also referring to feet. So we got negative 16 t squared plus the initial velocity again, which is 140 times the sine of 23 times t plus my starting position. And that's the spot, where does she hit the ball? Right? She makes contact 3 feet above the ball. So my thought is, if you can successfully set up an equation for horizontal and vertical movement, the rest of this stuff today is just really learning how to type it into your calculator. So question number 2 refers to the equations we set up. Where is the ball after 2 seconds? Well, 2 seconds is referring to t equaling 2. And the only question is where is the ball? Well, when they say where, we need to know both the horizontal and the vertical position. So I need to know how far did it go, and how high up. And if we wanted to draw a quick little sketch, you can picture Natasha right there, and clearly not going to be an accurate description, but there's when she hits the ball. So if you think of time, if time is equal to 2 seconds, the ball is somewhere in the air. How far horizontally and how far vertically is it? Well, all we do is go to the equations that we set up, and we're going to plug in 2 for the time. You do have to be careful with your calculator to make sure you are in the right mode, because anytime you have trig functions, you got to think, are you dealing with radians or degrees? So all I'm going to do is plug 2 into this function. And technically I could put plus 0 if I wanted to. And then evaluate it. So I'll give you guys a second. Go ahead and plug that into your calculator. Make sure that you are in degrees, because we're doing cosine of 23 degrees. So just to kind of quickly confirm, if I want to check the mode, I'm going to hit the mode button right next to the second key. And then I'm going to go down here and see that degrees are highlighted. If you use an online calculator, you might want to check that often, because I'm not positive if online calculators reset back to a factory setting or they stay on the setting you last used them on. I know mine doesn't. It's always in radians unless I change it. Alright, so once I have that, then I'm just going to enter it in. Notice my parentheses. If I forgot the parentheses around the 23, then I definitely would not get the right answer. And what does that mean? Well, that means after 2 seconds, the ball is 257.74 feet horizontally from where she hit it. So I might just save this answer quick. We'll come back to it. It's important to know that that's talking about the horizontal. So now, what about the vertical motion? Well, we're still going to do the exact same thing. We're going to plug in the y value at 2. Taking the equation we had written before. And I lost my room for the plus 3. So now you're going to type this in. Be very careful with the parentheses here. I'll show you. This is what mine looks like. Again, really the error a lot of times is not putting the parenthesis around the 23. And when you do that, you should get 48 feet. So if my drawing was at all accurate, which it's not, but that means the ball at 2 seconds would be about 257 feet. And then it would be up here at roughly 48 feet. That would be where the position of the ball would be after 2 seconds. And it's all because of the horizontal and vertical motion. Now we're going to have a little fun and look at some overall questions. How long was the ball in the air for? Well, what we need to know there, this goes right back to let me quickly move this get set up. There we go. So this is a rather famous question. If they ask for how long something is in the air, or another way to phrase that is, when did the ball hit the ground? Well, to do that, when did the ball hit the ground? What do you know about the vertical motion or the vertical position when the ball is hitting the ground? What is the vertical position when the ball hits the ground? 0. Right? It's 0, which means we're going to take the fact when y is 0. The ball hits the ground, that means that my equation for y has to be set equal to 0. So I'm going to take that equation with the initial velocity plugged in, with the angle of elevation plugged in, or the angle of projection plugged in, plus the starting height. And I have to solve that. Now, I could be really nice to you guys, or I could say solve that by hand. If you were to solve this by hand, this is a quadratic equal to 0. You could do quadratic formula here. Because you have an A, B, and C. We're not going to do that. But I just do want you to be aware, if you're doing the quadratic formula, there's your A, B, and C. And then you get to sing the song, x is equal to opposite b, plus or minus the square root, b squared minus 4ac, all over 2a. But we're not going to do that. We're going to let our calculator do the work. So, grab your calculator, and we're going to plug this into y equals. Instead of x, we're going to t, we're going to use x, and we're going to get a graph of this. So, I'll get you set up at least, hit y equals, and then let's type that in. Make sure when you use the negative, it's not a subtraction sign, it's the negative 16, and then just use x for squared, or for a variable, and then we'll square it. So I'll type in what I have because I need to see it. We're going to type in the equation. So just so you guys can see how I typed it in. Again, the parentheses around that 23 is really important. Now, even before I hit graph, I'm going to look at my window because we know something about this. There's real life context, and that can help us set a window even before we start. Oops, sorry. So there's the y equals. Anybody needs it? All right, so go to window now. And let's think about what each value means. X. Well, we said instead of t, we put x. So t is time. I can't really go back in time. So negative 10 seconds doesn't really help me, but I'm going to leave it. It doesn't matter. X max is referring to the time that the ball would be in the air. I don't think that somebody would hit a ball and it would be in the air for 10 seconds. So I think 10 seconds is plenty enough time to see the motion. The y minimum refers to your lowest value, and we want to see when it hits 0. So I'm going to leave it at negative 10, but it's my x maximum that might be of interest to me. And the, y maximum, that's how high the ball goes. We know at 2 seconds she hit it and it was like 48 feet in the air. So I need to be higher than 48, and I always just kind of overestimate. I really doubt that somebody could hit a ball 100 feet in the air, but I'm going to put it as 100 feet. And that's going to hopefully give me a nice graph that we need. Hit graph. And that's plenty. You can definitely see the maximum height of the ball, which we could find that if we wanted to. But what I'm really interested in is where does it hit the ground? When is y equal to 0? So if you remember this from Algebra 1, Algebra 2, we're going to go second trace. That's the calc function. And we're going to go down to 0. So just a quick refresher, second trace, and then we want to find the 0. Okay, and then hit enter. And what you need to do is you need to take your cursor. That's the flashy little thing. And here's how I tell students to do it, because it's telling me to set up a left bound. This is the way I think of left bound, is if I go to the spot where I think the answer is, if I get as close as possible, left bound is hitting the left arrow a couple of times from that. So hit the left arrow a couple times, and that'll give you your left bound. Hit enter. And then it says right bound. Well, a right bound has to be to the right of where we think the 0 is. So then I'm going to go to the right a couple of times, and it's okay if I go off the screen. And then when it says guess, just hit enter. You don't have to do anything for a guess. And notice, this is an interesting answer. I want to know when the y value is 0, but they don't give me exactly 0. They give me scientific notation that is telling me to take a decimal spot and move it 11 spots to the left, which is basically 0. So when you see this scientific notation, it means 0. Okay? It's just your calculator can't get to the actual 0. All right, so how long does it take? How long was the ball in the air for? 3.47 seconds. And it's always a good idea to round it to 3 decimals. You'll start seeing that in calculus. Okay. So the last question. Does Natasha hit a home run? What do you think? What are you wondering right now? Awesome. How big is the field, right? That's way too vague of a question right now. Does she hit a home run? Well, we don't know. We don't know how big the field is, and we don't know how tall the fence is. So we have to you can't answer questions until you know all the details, and that's part of the reason why I just kind of left that one, so we could think about that. Let's say that the distance from home plate to the outfield fence is 220 feet, and the wall is 12 feet tall. Well, we know how long it's going to take for the ball to hit the ground. We know that at 2 seconds, she already traveled 257 feet. So she's definitely past the vertical or the horizontal motion. But where is she at 2 seconds? Or actually, let's do this. Let's find that at 2 seconds. Let's find the vertical motion and see. Actually, you know what? Let's do this a little bit differently. Let's figure exactly how long does it take for the ball to hit the fence. So what we're going to do, if this is the horizontal motion, we're going to take that horizontal motion and set it equal to the x equation. We kind of did this with the baseball one. Here's my x equation up here. We're going to put 220 here, and then we're going to solve for t. So 140 cosine of 23 times t. And I'm going to show you something really helpful with your calculator that I just learned maybe a year ago. And I often forget to use it, but I think it's something you might really like. So algebraically, we have to solve for this. I need to get t by itself, which means I'm going to take and divide both sides by 140 cosine 23. You have to be very careful when you enter this in. So we're going to take 220 feet, we're going to divide it, and if you want, you could put parentheses around that. I already forgot what it was, 110? 140 times the cosine of 23. So that's how long it's going to take for the ball to reach the fence itself. Now, here's the part I want to show you something new. That's kind of a long answer, right? And you could round that to 1.7. But watch this step. I can store this answer into my calculator. I don't know if you guys have ever done this or been made aware. See the button right next to the one? It says STO with an arrow. Click that, and it's going to say you want your answer stored, and then we get to pick. So we get to pick a letter. So we're going to do the green button alpha, and let's call this A. So go alpha, A, and then hit enter. So now this is logging it in, so I don't have to retype that whole thing. So anytime I want to use A, or this answer, I can just call it A instead. Now, what do we want from this? Well, I know how long it's going to take to reach the wall, but now I want to do the height. So I'm going to take the y equation, and we're going to plug in where t is. We're going to plug in that a value, 1.7, that whole thing. So let me see if I can memorize this. I might have to ask for your help. Let's go negative 16, and then I want to times it by the a value, which go alpha a. Then we have to square it. And I already forgot. It was 1 plus 140. So plus 140 times the sine of 23. And then I have to times it by the time again. So instead of putting that whole number in, use A again. Alpha A plus your starting height of 3. And if you hit enter, that tells you where the ball is exactly at that time. So let me pull this over just so you guys can see it. So we did all this work to find the time, and then this is to find the actual height. So if the wall is 12 feet tall, and it took 1.7 seconds to reach the wall, and at the time her height was 47 feet, did she hit a home run? She crushed it, right? If the wall's 12 feet, she's way over that, so she hit the home run. Home run. So hopefully you can see how, okay, we can use the x equation to find the time that it took to get to somewhere, and then once I know the time, I can use it in the y equation to figure out the actual height. And that allowed me to make a conclusion. We're going to do almost the same thing with a different type of example here, and hopefully that will give you enough to be successful in the homework today. This first example was definitely much longer. This next one should be fairly quick, and I think I'm going to have you guys try it once we set it up. All right. I'm not sure if you follow hockey at all, but the Minnesota Wild have I think a potential superstar on their hand, and there's a guy named Kirill Kaprizov who has just taken the league by storm. So, Kirill takes a slap shot from 40 feet away from the goal with an initial velocity of 80 miles per hour. When I was making this equation, I actually did some research, and it said the average shot is anywhere between like 70 and 80 miles an hour. Some of them can be up to 100 miles an hour, which tells me I would never want to be a goalie in hockey. The puck leaves the stick at an 8.1 degree angle. Our question is, if the standard NHL hockey net is 48 inches tall, does the puck land in the net, assuming that the goalie doesn't stop it? Well, we have to be careful of a couple of things here, and I'm wondering if you guys notice anything in this description up here. Does anything bug you or make you a little concerned? What's that? Yeah, I guess, he could be moving, or he could be sitting still. Let's assume he's sitting still, because otherwise, his movement would change it completely. But let's assume that he's just shooting it, the puck's coming, and then he hits it, and all the data is from the moment that he hits the puck. But look at the information that's given. We have the distance that he is away. So let's assume that the puck is right here. And then he hits the puck. And it's 43 feet away. Now we don't know exactly where he's going to hit, but the puck is going to go in the air. at 8.1 degrees. And we're wondering how tall it is. Where does he hit that? But then they give me a rate. They give me the velocity, which is 80 miles per hour. Miles per hour. Miles. Are we concerned about miles at all in a hockey arena? No. Look at the measurement. We know we're 43 feet away. So what we have to do is we have to be aware of the rate and make sure that the rates are in the same expression. So this would be if you were doing a real example here, and you actually wanted to find this for real life, here's what I would do. Convert miles an hour to feet per second. So I'm going to take, if he was doing it at 80 miles per hour, we're at 117.333 feet per second. So we have to be very careful when they give us something. And I'll just share with you, we're not going to try to trick you on that, but I always want to kind of put that in your back pocket of, think of units. Units mean something, and you may have to do conversions. Oops, I put the wrong thing. It's not beta. That's the velocity. So that's the velocity we need. So now we have kind of everything we need. Does the puck land in the net? Well, we need to know a couple of things. The ultimate goal is to figure out how high does the puck go. But I can't tell how high the puck goes until I know how far, or I should say how long it takes to get to the 43 feet. So we have to find the time first. And once I know the time, then I can apply that to my vertical motion. So that's where we're going to start. Okay, let's start off with the x equation. The horizontal distance is given by the velocity times the cosine of the angle times the time. All right. Now, we don't know the time, right? That's what we need to find. But I do know, of course, this is slowing down. I do know that I'm going 43 feet. So that's my ending result. I want to put 43 feet in the output and then work backwards to find the time. And that's basically the exact same thing we just did with Natasha and her home run. So I want to see if you guys can take it from there. So what we need to do is we need to take this information and solve for t. So I'm going to divide both sides by to divide both sides to get t by itself. And this is where I would do a lot of this in my calculator. So I'd take 43 divided by 117.33 times cosine of 8.1, and you'll get the time to be just over a third of a second. Right? That's happened really fast. So now, if you would like, you can use this feature and store this in your calculator. I'll show it to you again. I'm going to hit store, and then I'm going to go alpha A, or I could call it B, it doesn't matter, but I'm going to go alpha A. So now this is what A is equal to. That just saves time typing it in. But how am I going to use that equation? Let's point through that. Well, I need to set up my vertical motion equation. So I need to set up the y of t, and that was negative 16 t squared plus the initial velocity times the cosine of the angle t, and then you got to think about this here. What's my initial height? It's a hockey puck. 0, right? We're going to put plus 0. The hockey puck is on the ground when they hit it. Oops, that should be sine, not cosine. Yep. And then my goal is to plug the t value that we just found in here. And I'm going to do that in my calculator. See if I can memorize all that, type it in. So we got negative 16, and then again, I called my answer A. So I'm going to go alpha A. I'll square it. That's not a squared. Square it. And then we're going to add the velocity times the sine of the angle, 8.1, times A. We got times by that time again. And then if you want, you can put plus 0 to represent the original starting height. What does that answer mean? Because there's context to this problem. The y value is the vertical height, and we plugged in the time of 0.37 seconds. So what this answer is this is the height then. And the question now is, if the standard NHL hockey net is 48 inches tall, did the puck land in the net? What do you think? What's that? Got to convert feet to inches, right? Again, here's another conversion. 48 inches tall. Well, how many feet is that? 12 inches is a foot. 12 times 4 is 48. So this is really saying that the goal is 48 feet. Just under, or 4 feet, sorry. Just under 4 feet. So Kirill Kaprizov scores the goal. So does the puck land in the net? Yes. And it's just going to sneak under that crossbar, which is one of the best shots in hockey, right? Because the goalie can't get up that high. And that kind of shows you the talent and skill of these professional players. Same thing with the softball. So that's just how we can use these equations. Really, the big reason why we're doing this, to teach you algebra skills, to teach you how to do it in your calculator, and then problem-solving skills about converting units if needed. So I hope you learned something new with your calculator as well today. I wish I would have known that years ago. You can always store an answer in your calculator and then use that letter that you called it to help simplify some things. All right, let me show you this last slide and then you guys will be good. So a reminder, this week we kind of scrapped what we did on Tuesday because Schoology being down. Today we readjusted. We tried two new problems. On Schoology there's a worksheet 6.3 day 2 homework. You have to click on there and it's just a PDF. So you'll be able to pull that up and there's 3 problems very similar to what we did today. I think they're actually a little faster. The answers are in Schoology as well. There's a homework for a sheet that folder that you can view those answers and check your work and then submit that. And then the big thing, and I hope everybody on Zoom hears this, we have a quiz tomorrow. The quiz is in Schoology, so you have to access the folder and then open that up, and you are also asked to submit your workout solutions after you take this should say quiz, after you take the quiz. All right, so that's the expectations for tomorrow. So homework tonight, you can check your answers in the Schoology folder, submit your work. I'll even show you here, because we don't do a lot of work in Schoology, so, oops. See the second folder in? Homework answers. Click on that. Today is 6/3, day 2. It's right there. So check your answers. Don't use that to copy, but use it to check. All right, that's all I got. Everybody on Zoom, have a wonderful day.